in the actual reaction mixture. So let me show you an actual problem here. Let's go through one where this will be the case. So let's say I start with an acid chloride. And I'm going to react it with, this is, of course, has all been in basic conditions with negative charges. On your class notes, we talk a lot about basic conditions, right? That's the first one we actually talk about. So an overall negative charge. So here the first step is we attack the electrophilic carbon of the carbonyl group. Electrons go up. These are all equilibrium arrows. We went from sp2 to sp3 now that carbon did. Balance my charge. Tetrahedral intermediate. Now you have a choice. Which one's the better leaving group? In this case, chlorine is the better leaving group. All right, so we'll take that and kick the chlorine out. We've remade the pi bond, so this is our elimination step. This was our addition step. Now we've turned what was an acid chloride into an ester with Cl minus. And again, now why would this happen? Well, Cl minus is more stable than O minus. That's why this would go. You can think of cases where it'd be less likely to. So let's say I have an amide. And I'm going to react this with I minus. Alright, so let's move this stuff up a little bit. With I minus. Now, I can just shrink that down actually now. Move that there. Again, I minus can attack. Right, but again, I minus is not great of a nucleophile, and amides are pretty stable because of the possible resonance, which I don't have drawn here, because nitrogen is willing to do that. So let's say this equilibrium lies, right, really more towards the reactants. We get some of this, right? We say we get some of this. But the likelihood, the best leaving group here still is, right, the best leaving group here actually is the I minus. So you actually just go back to what you started before. And really, if I redrew this, there'd only be a very, very small amount, right, of this actually happening, where these electrons come down, we kick out what would be, right, it'd be a very small arrow, what would be essentially N minus, right? That won't be very stable at all. And if anything, it's just going to react and go backwards again and essentially repeat the process, right? So it does matter on how stable the nucleophile is and also how stable the leaving group is, right? All right, showing here a basic SN2 slide. Now don't be confused, we're not doing SN2 reactions. The point of this is, right, what bond do we usually break? We always usually break the weakest bond. So what's the weakest bond on a carbonyl group, right? That, of course, is the pi bond. So that's the bond we want to break. All right, so what does it look like? Molecular orbitals. So if the pi bond, right, looks like this. Actually, I'm going to draw it a little even a little more pronounced. Let's get a little more pronounced with this. Let's make this make sense. Right, so there's a carbon and an oxygen. Where do you think most electrons are at in the pi bond? I would guess they'd be around the oxygen. So that should be a bigger orbital, a bigger lobe. The carbon has some, but just not as big. And this is pronounced, right? And that's where they're bonding, right? Most electrons in the pi bond, right, in the pi bond are over by the oxygen. So if we start looking down here at pi star, well, guess what? Where's the bigger lobe at now? Now the bigger lobe, of course, is by the delta plus carbon, right? Now if I want to break a pi bond, I need to put electrons in its pi star. And so here comes the nucleophile attacking the pi star, right? As they put electrons in that pi star, what happens to the pi bond? It, of course, breaks, right? So that's what they're trying to highlight here. All right, one thing I'm not oblivious to, the chlorine does have lone pairs, right? It can do resonance, but how likely is the chlorine to give up those lone pairs? Not very likely. That's the difference. Base, but I would say I minus is more stable than Br minus if you put those in here as well, right? You could think about where that leaving group hierarchy was before. But basically, this is saying is what are good leaving groups? What is the most stable thing, right? It's going to be hard to work backwards, right? N minus is not a good leaving group. O minus is not a good leaving group. Cl minus is, right? So what becomes most reactive? When we say reactive, we are talking about this carbon, right? We're talking about this carbon, right? Which carbon is most delta plus, right? Remember, these guys can all do resonance, right? They can do resonance of varying degrees. And resonance makes that carbon less reactive, right? So it's easy to go turn acid chloride into an ester, but it's probably hard to turn an amide back into an acid chloride, right? It's easy to go downhill, right? Reactive to something less reactive. Hard to go something less reactive and make it something more reactive, right? It's all about, right, how delta plus these carbons are and how good of a leaving group you have attached there. Again, just highlighting, remember, if you can do resonance, that's going to make this carbon less reactive, which is going to make this, those acid derivative, carboxylic acid derivatives that can do resonance much less reactive, right? I would, again, overemphasizing here, the best leaving group when you're in the tetrahedral intermediate, again, tet intermediate, now you have a choice. These electrons are coming down. Which group is the best leaving group? Which one's going to be the most stable? That's the one you kick out most of the time. Now this is just kind of highlighting the mechanism I showed before, right? Now remember, this is not SN2. This is a addition elimination mechanism, right? We can't do SN2s on sp2 hybridized carbons. But if you look at this, the big difference here is this versus this. Which one is a more stable with a negative charge? The chlorine is, so this reaction will go forward. Whereas here, right, Cl minus, right, is pretty happy. And this is not that great of a leaving group, so there's going to be no reaction in this case. But again, not SN2, additional elimination. We need to have a better leaving group, or more stable products than reactants, or a better leaving group is also a way to say it. Reaction coordinate diagrams, kind of highlighting these things. I wouldn't worry too much about, right, the intermediates. That's not the important part. But if you look here, you have a less reactive, a more stable compound. So like say something like an amide for a starting material. So you have an amide for a starting material. That's pretty stable. That's not going to want to turn into a ester. Let's say you have an ester, you're going to be probably, you'll be able to turn that into an amide. But let's say you start out with an ester and want to turn it into a acid. Both of those are about the same, right? Amides are more stable, worse leaving group than an ester, so it'd be an uphill process, poor leaving group, right? Nitrogen would be a bad leaving group. Again, here, an ester to an amide would be a downhill process. Esters are more reactive, have a better leaving group than an amide. Then an ester and a carboxylic acid are about the same. An OH minus and an OMe minus about the same reactivity. So that's what we can look at as a free edge diagram. And to wrap up, to emphasize this again, if you look here, obviously we have our nucleophile attack the carbon of the carbonyl. So this would be the addition step. Right, we can't do SN2s on sp2 hybridized carbons. This is still sp2. Tetrahedral intermediate, so the tet intermediate. This carbon is now sp3. We kick out the better leaving group. Y minus must be more stable, right? Less reactive than the CHO3 minus. Right? And that's the negatively charged. We've done anything so far as negatively charged situation, adding to a carbonyl carbon. So what about the case if we're not using basic conditions? What if we're using neutral? So that means I don't have an overall plus or overall minus, but I'm overall neutral. What would happen if I take something like this and just put it in methanol? What is that going to look like, right? Again, the nucleophile attacks, adds to the carbon of the carbonyl group, which is delta plus, right? We are sp2 here. So this is the addition step. Now we're sp3 in that carbon. We have to look at what leaving groups are around. So when we say base here, I would assume base could just mean another molecule of methanol. This is usually, I would usually say this is the solvent. And that's usually the solvent. So let's just replace this guy with that. Alright, so HB here would just be CH3. Alright, so the solvent's kind of helping move that proton around. And now once you've been deprotonated, right, once the H has been taken off, right, because at this point, right here, this is still the best leaving group. It has a plus charge, right? Leaving groups with plus charge is really good. But taking that H off, now it changes things. Right, so we call this a proton transfer, and this is transferring to the solvent this time, which is this. Now, a tetrahedral intermediate, so tet and tet. Now we have a choice here, either Y or OCH3. In this case, Y is going to leave, and we eliminate the weaker base. So what I would say here is, let's pretend Y is just Cl minus. Let's pretend Y is Cl minus. So Y equals Cl. Y equals Cl, not Cl minus. Y minus equals Cl minus, and Y equals Cl. Right? So in that case, Y, especially in this situation, is going to be a better leaving group. So just translate Y for that. Alright, kind of moving along here. Still thinking about esters. We've kind of focused in on